Imagine this. You eat breakfast in New York, and just 90 minutes later, you're sipping afternoon tea in London. This isn't science fiction. It's a real engineering pursuit that's becoming reality. The United States is now building a hypersonic aircraft so fast, so radical, it doesn't just challenge fighter jet conventions, it shatters them. At the heart of this revolution lies a new generation of American aerospace engineers with a singular mission: to bend the laws of physics and rewire the definition of speed. This is the story of the US hypersonic jet design that breaks every rule of fighter jet physics. Hypersonic flight begins at Mach 5, 5 times the speed of sound, or about 3,836 miles per hour. At this velocity, even the air becomes a formidable enemy. The friction generated as the aircraft slices through the atmosphere doesn't just create drag, it produces a level of heat so extreme that it can melt aluminum like butter and even compromise the structural integrity of titanium. This isn't just an aerodynamic challenge, it's a thermodynamic nightmare. The moment you push into hypersonic speeds, the very sky becomes a battlefield of physics. Traditional fighter jets, like the F-22 Raptor or F-15 Eagle, have served as the backbone of American air dominance for decades. They are fast, agile, and deadly, but even their cutting-edge engines hit a wall around Mach 2.5. Beyond that, turbine blades overheat, airframes vibrate uncontrollably, and airflow becomes chaotic. The cost of pushing further has always been considered too high. For decades, engineers accepted this Mach 2.5 ceiling as a fundamental law of manned aviation, a red line drawn by physics itself. But not anymore. We are now witnessing the dawn of a new aerospace revolution, a revolution not driven solely by government contracts or defense budgets, but fueled by the relentless innovation of private companies willing to take risks. A new breed of aircraft, born from the collision of military precision and Silicon Valley's fail-fast ethos, is preparing to cross the hypersonic threshold. These aren't rocket-powered spacecraft or disposable test beds. They're real, runway-launched jets designed to pierce the sky, cruise through the upper atmosphere at blistering speeds, and return to Earth under their own power. This is the future of flight, and it's arriving faster than anyone expected. To understand what makes this moment so extraordinary, we need to revisit an old legend, the Lockheed SR-71 Blackbird. This wasn't just an aircraft, it was an engineering myth made real. Developed in secrecy during the Cold War by the legendary Skunk Works division at Lockheed Martin, the SR-71 first took to the skies in the 1960s with a mission unlike any other: to fly faster and higher than anything else in the sky and do it without being shot down. In 1976, the Blackbird officially set the airspeed record by reaching Mach 3.3, roughly 2,193 miles per hour. To this day, that record for manned air-breathing jet aircraft still stands. The SR-71 didn't just fly fast, it flew so high, above 85,000 feet, that enemy surface-to-air missiles couldn't touch it. And even if one was launched, the Blackbird could simply outrun it. The Blackbird was a technological marvel, far ahead of its time. Its body was made primarily from titanium, sourced covertly from the Soviet Union, because no other material could withstand the intense heat generated at Mach 3 speeds. It had no digital computers. Everything was analog, navigated with celestial guidance systems, and managed with hands-on controls. The aircraft expanded nearly a foot in length due to the heat during flight, and fuel leaked on the runway until the skin sealed midair from thermal expansion. And yet, despite all its accomplishments, the SR-71 remained a lone peak. For nearly 5 decades, no one seriously attempted to build anything faster. The challenges were just too immense. Faster speeds meant exponentially more heat, greater material stress, and a need for completely new propulsion systems. Governments and contractors shelved the idea, content to live in the shadow of the Blackbird. Until now. Now, a new generation of engineers is rising, not to imitate the Blackbird, but to surpass it. They're not just trying to break its speed record, they're rewriting the rules that once defined what an aircraft could do. The era of hypersonic flight isn't coming, it's already begun. The monster engine, Chimera. Enter Hermeus, a scrappy aerospace startup based in Atlanta with a bold mission to make hypersonic flight routine. Born from a mix of former SpaceX, Blue Origin, and NASA engineers, Hermeus isn't just tinkering with new designs, they're trying to redefine the physics of flight. Their answer to the hypersonic challenge, a revolutionary propulsion system known as Chimera. Chimera is no ordinary engine. It belongs to a rare and highly complex class of propulsion systems known as turbine-based combined cycle engines, or TBCCs. In simple terms, it's 3 engines merged into one seamless unit: a turbojet for low-speed operations and takeoff, a ramjet for high supersonic cruise, and eventually a scramjet capable of propelling the aircraft beyond Mach 5 into the hypersonic domain. It's a mechanical shapeshifter, capable of evolving mid-flight to match its environment. But making these radically different propulsion modes coexist inside a single engine is like trying to build a race car, a rocket, and a stealth bomber in one frame. A turbojet works with spinning compressor and turbine blades, generating thrust by compressing air before igniting it with fuel. A ramjet has no moving parts. It relies entirely on the aircraft's forward motion to compress air. And a scramjet, that's even more exotic. It must ignite fuel in an airstream moving faster than the speed of sound, something akin to lighting a match in a hurricane. The hardest part isn't operating each mode, it's transitioning between them. The moment when the engine must shut down its turbine-based core and allow hypersonic airflow to bypass the compressor entirely is known as the aerodynamic valley of death. If the switchover is even slightly mistimed, the entire engine can choke or unstart, causing a catastrophic loss of thrust and potentially tearing the aircraft apart. It's the Achilles heel of hypersonic propulsion, and one that has defeated military contractors for decades. Hermeus didn't back down. Instead of relying solely on simulations and theory, they went hands-on with a hardware-first approach. In November 2022, at the University of Notre Dame's Turbo Machinery Laboratory, Hermeus conducted a breakthrough test that shook the industry. Chimera successfully transitioned from turbojet to ramjet mode in a ground test simulating Mach 4 airflow. This wasn't a concept sketch, it was real, fiery hardware proving its worth under intense thermal and pressure conditions. That moment cracked open the door to a new era, one where hypersonic aircraft can take off from runways, accelerate past the speed of sound, and reach Mach 5 without boosters or rocket stages. Chimera isn't just an engine, it's the mechanical heart of a revolution. Flying at Mach 5 isn't just about having enough engine thrust, it's about enduring a hellish environment where physics constantly tries to tear the aircraft apart. At hypersonic speeds, the aircraft doesn't just cut through air, it slams into it with such force that the very air molecules break apart, generating intense frictional heating. The nose of the aircraft, as well as the leading edges of its wings and control surfaces, can reach temperatures exceeding 3,000 degrees Fahrenheit. That's hotter than the molten core of a volcano, and far beyond what traditional aerospace materials can handle. Aluminum, the go-to material for commercial airliners, melts at just over 1,200 degrees Fahrenheit. Titanium, favored for its strength and light weight, begins to soften and lose structural integrity around 1,800 degrees Fahrenheit. Even advanced carbon fiber composites can degrade or delaminate under such intense thermal stress. This is where hypersonic flight pushes us into the bleeding edge of material science. To survive this airborne inferno, Hermeus turned to carbon-carbon composites, a material so resilient it was used on the space shuttle's nose cone and wing edges, where temperatures routinely exceeded 2,500 degrees Fahrenheit during re-entry. These composites not only tolerate extreme heat, but maintain structural rigidity when other materials would disintegrate. To bolster high-stress areas, such as engine intakes, wingtips, and control surfaces, Hermeus employed ceramic matrix composites, which offer both high temperature tolerance and resistance to thermal shock. But the real marvel lies deep within the engine itself. Hermeus uses Inconel 718, a high-strength nickel-based superalloy that resists oxidation and maintains its integrity even under severe thermal cycling. They 3D print critical components, such as heat exchangers and turbine housings, with Inconel, taking advantage of complex geometries that would be impossible to manufacture using traditional methods. These printed parts form the skeletal structure of Chimera's pre-cooling system, the unsung hero of hypersonic propulsion. The pre-cooler is nothing short of a miracle component. As the aircraft moves at supersonic speeds, air entering the engine can exceed 800 degrees Fahrenheit before it even reaches the combustion chamber. The pre-cooler rapidly chills this incoming air down to a safe, stable temperature in milliseconds. This prevents the turbine blades from overheating and allows the engine to breathe like a calm marathon runner, even as the vehicle rockets through the atmosphere. What Hermeus has engineered is nothing less than a thermal ballet, a delicate dance where every component must survive fire and friction, velocity and vibration. At Mach 5, the air becomes fire and flight becomes survival. Thanks to cutting-edge materials and ingenious engineering, Hermeus has made it possible to not just fly through this gauntlet, but to thrive in it. With the Chimera engine finally proven in testing, Hermeus faced the next formidable challenge: building an aircraft that could harness that power and survive the extreme demands of hypersonic flight. This required more than just aerodynamic finesse. It demanded a complete reimagining of materials, flight control systems, and structural resilience. Their approach was methodical and aggressive, progressing through a series of increasingly capable platforms. The journey began with quarter-horse Mk-0, a ground-based test rig affectionately referred to as the Iron Bird. Mk-0 never left the runway, but it played a critical role. It validated remote command and control systems, tested avionics, and provided engineers with real-time telemetry data on software integration and RF latency. These are not glamorous tasks, but they are foundational, especially when designing a vehicle that will operate at 5 times the speed of sound. Next came quarter-horse Mark I, a sleek subsonic demonstrator aircraft that marked Hermeus' first true step into flight. On May 27, 2025, at the legendary Edwards Air Force Base, Mark I took to the skies. Its mission was focused: prove the basics, high-speed taxiing, takeoff and landing dynamics, control surface response, and aerodynamic stability. Even at subsonic speeds, these data-rich test flights yielded valuable insight into how future airframes would behave when pushed to the limits. But the real action begins with quarter-horse Mark II, roughly the size and shape of an F-16 fighter. Mark II incorporates the battle-tested Pratt & Whitney F-100 engine, the same afterburning turbojet that powers the F-15 Eagle and F-16 Fighting Falcon. But this engine has been supercharged by Chimera's integrated pre-cooler system, allowing it to operate efficiently at far higher speeds than originally intended. Mk2's objective: shatter the sound barrier and sustain stable supersonic flight just shy of Mach 3. This aircraft marks the first real-world testbed for validating Chimera's performance in high dynamic pressure environments. Then comes the crown jewel, quarter-horse Mark III. This is Hermeus' record-breaking platform. Designed to exceed Mach 4, Mark III will be the first aircraft to demonstrate full TBCC engine transition, from turbojet to ramjet, in the air. If successful, it will dethrone the SR-71 Blackbird as the fastest air-breathing manned aircraft in history. Mark III is more than a test vehicle. It's a bridge to the hypersonic future, where propulsion systems morph mid-flight and sustained Mach 4+ cruise becomes reality. But Hermeus isn't stopping there. Their ultimate vision is embodied in Dark Horse, a fully operational, autonomous, hypersonic UAV purpose-built for military applications. Dark Horse is engineered for high-risk, high-reward missions: intelligence gathering, surveillance, reconnaissance, ISR, and precision strike deep within contested airspace. Capable of launching from conventional runways and reaching theaters of operation in minutes, Dark Horse is the Pentagon's ace in the hole for future conflicts. In a world where hypersonic speed means survival, the Quarter Horse series is the proving ground, and Dark Horse is the execution. Together, they represent a seismic shift in the philosophy of military aviation: faster, cheaper, modular, and operationally flexible. From subsonic Iron Bird to Mach 5 warfighter, Hermeus is building not just aircraft, but an entirely new class of airborne dominance: strategic shockwave. The implications are enormous, nothing short of a paradigm shift in modern warfare. Hypersonic aircraft like Dark Horse don't just represent a new category of vehicle, they redefine the tactical and strategic playbook of the US military. In a world where speed compresses geography, Dark Horse can fly from Guam to the South China Sea in under 30 minutes. That's faster than most battle plans can be updated. At these velocities, time itself becomes a weapon. Flying at altitudes above 80,000 feet and at speeds exceeding Mach 5, Dark Horse operates in a regime where very few systems can follow. Modern surface-to-air missile systems like Russia's S-400 or China's HQ-19 are designed for slower, more predictable targets. At hypersonic speeds, reaction windows shrink to seconds, radar tracking becomes unreliable, and intercept paths collapse before they can be calculated. In effect, Dark Horse becomes untouchable. It arrives, delivers its mission payload, and vanishes before an enemy commander even knows it was there. But it's not just about flying fast, it's about strategic positioning. In the newly formulated US military doctrine of 2026, platforms like Dark Horse are referred to as first-in enablers. Their mission, to kick down the door before anyone else arrives, whether it's blinding enemy radar with electronic warfare, jamming communications, launching precision strikes on anti-aircraft defenses, or performing ISR, intelligence, surveillance, and reconnaissance, deep within contested airspace. Dark Horse makes it possible for slower, stealthier platforms like the B-21 Raider or 6th generation NGAD fighters to survive and complete their missions. This is the fusion of speed and strategy. Speed becomes stealth, velocity becomes survivability. Unlike traditional stealth platforms that rely on shaping and radar-absorbent materials, Dark Horse weaponizes time. It's not just hard to see, it's impossible to catch. In this new age of warfare, evasion isn't achieved by hiding, but by arriving too fast to be targeted. As the Pentagon's latest doctrine states, win the opening minutes of the war, and you win the war. Hypersonic platforms like Dark Horse are designed to do exactly that: seize the first 5 minutes of combat, dismantle enemy defenses, and dictate the tempo of the conflict. They're not just aircraft, they're shockwaves, fired across the sky at 5 times the speed of sound. And in this high-stakes chessboard of 21st century warfare, Dark Horse is designed to move first and strike hardest. Hermes isn't alone in this race, but they may be the fastest out of the gate. Across the aerospace landscape, major players are scrambling to lay claim to hypersonic dominance. Stratolaunch, for instance, is actively testing its Talon A hypersonic vehicles, small rocket-launched platforms designed to reach Mach 5 and return valuable data for defense customers. Meanwhile, Lockheed Martin's highly secretive SR-72, son of Blackbird, is believed to be undergoing classified flight trials at test ranges in the Nevada desert, continuing the legacy of the legendary SR-71. Even the US Air Force has quietly restarted its once-shelved Project Mayhem, an ambitious program to develop a reusable, multi-role hypersonic platform capable of surveillance, strike, and deep penetration missions. Each of these programs represents a different vision of the hypersonic future. Some rely on rocket propulsion and air launch systems, others are pushing scramjet-only designs that operate at the edge of Earth's atmosphere. But Hermes holds a critical and potentially game-changing advantage: runway independence. Unlike rocket-boosted designs that require launch towers, mothership aircraft, or expensive logistics footprints, Hermes's Quarter Horse and Dark Horse vehicles are built to operate like traditional jets. They can taxi, take off, and land from standard military airstrips without any exotic support infrastructure. This dramatically reduces operating costs, accelerates deployment timelines, and enables repeatable missions with fast turnaround. It's this modularity and self-reliance that has captured the attention of defense leaders and investors alike. Hermes's approach isn't just about building a hypersonic aircraft. It's about making hypersonic flight practical, affordable, and scalable. And now the spotlight shifts to their most daring test yet: Quarter Horse Mark III. MK3 is the high water mark of Hermes's current development roadmap. The objective: achieve mid-air transition from turbojet to ramjet propulsion using the Chimera TBCC engine and sustain controlled flight at speeds exceeding Mach 4. This would be a landmark achievement, the first successful demonstration of full TBCC transition under real atmospheric conditions. No wind tunnels, no simulators, just sky, heat, and velocity. Hermes refers to this upcoming milestone as the bridge, not just a technical achievement, but a symbolic crossing, from the limitations of 20th century jet propulsion to the boundless frontier of the hypersonic age. If Quarter Horse Mark III succeeds, it won't just break records. It will validate an entirely new model of aviation: reusable, runway-launched, air-breathing vehicles that rewrite how nations think about speed, power projection, and global reach. So what happens next? Will 2026 be the year the Blackbird's record finally falls? Can hypersonic travel become routine, not just for military missions, but one day for civilians too? Will you someday fly from LA to Tokyo in 90 minutes? The engineers at Hermes believe so, and they're proving it step by step. Let us know your thoughts in the comments. Are we ready for Mach 5 flight, or is this technology destined to remain military only? Don't forget to like, subscribe, and hit the notification bell so you don't miss our next top secret defense briefing. Thanks for watching Jet Hub. We'll see you in the stratosphere.